Thanks for joining us today. My name's Dave Corney, and I'll be introducing Alexander here. Alexander Wolf, he is with Frankensolar. Graduated from the University of Stuttgart, Germany, with a master's degree in electrical engineering with a focus in power electronics. Started his career in renewable energy in 2011 in Germany. As a hardware developer for three-phase commercial string inverters, and was involved in the design of string inverters with total worldwide installed capacity of about 5 gigawatts. As their product and solutions engineer, Alexander is responsible for bringing new products to the company's portfolio, which meets Frankensolar's strong focus on high-quality equipment and customer-specific innovative system solutions. He's also responsible for Frankensolar's in-house project engineering for commercial grid tie and off-grid solar PV systems. So take it away. I don't think there'll be any rush for time. You're the only presenter here. You've got 50 minutes. Maybe leave a good period of time for questions. Great. Thanks.
Thank you very much, Dave. My name is Alexander Wolf, as I already announced, I work for Frankensolar, and we are a Canadian distributor, formerly out of Germany, that sells solar systems and equipment nationwide from coast to coast to coast, also, of course, here in Atlantic Canada. My presentation today is about inverters, as you can see on your schedule. And we want to look into how we can design systems for best performance and best economics. Designing system for best economics, one key part is the oversizing. So how much DC, solar panel capacity, are you connecting to your inverter at a certain AC capacity? We want to have a sample analysis of the yield of multiple systems and then compare these systems and their respective system cost to what the ROI would be for the customer, so the end customer who owns the system. We also talk about understanding the system limits, so how far can you actually push that oversizing? And we will talk about a little bit of myth that is still in the market, I hear once in a while. When you have oversizing, where is that power actually going that is not being taken by the inverter? The second main topic in this presentation is about MPP tracking, more specific about shade and shade mitigation in MPP tracking. There's a topic or a technology called global MPPT tracking. And as a few sub-questions, we have the question, what happens if one panel is shaded? There's still that marketing push from a few American companies that if one panel is shaded, your entire string is not working. We will get rid of that myth once and for all. Second topic, how does MPP tracking work for conventional systems, and how does global MPP tracking work as a more advanced algorithm? And then at the end, we want to go over where are the applications for regular string designs with that algorithm, and where are you better off using an optimizer or a microinverter for very complex shading scenarios, for example. So first of all, just to set the base, what is DC to AC ratio? Very simple. It's the total sum of all the DC of your solar modules and in relation the inverter's AC nameplate capacity. Very quick picture here. We have a sample system of, let's say, 12 kilowatts, 30 modules, each 400 watts, and we connect that to a, for example, 10 kilowatt inverter. At that point, simple math, 12 over 10 is 1.2, so our DC to AC ratio is 1.2 to 1, just as a very quick start. When we look into designs today, what really matters for the customer is not how technically perfect and how technically efficient your system is. What matters for the end customer is how low can you produce the power. So what's the lowest cost per kilowatt hour that you as the installer can provide to the customer? And at the end of the day, the solar system a customer wants to have installed is always competing against power he would otherwise buy from the grid. In order to do a sample system and the analysis, we have to start with a few assumptions. And since it's a very good building block, I just picked the 10 kilowatt inverter on the AC side and its AC connection that is related to that. In my example, it's just two SMA inverters. We have to specify a certain electricity rate that the customer is comparing his system to. I just picked 18 cents. I saw in Nova Scotia we're between 16 cents if it's a tiered system or 20 cents if it's on peak. So 18 cents in the middle is roughly there. And very specific, the sales price for the customer for the first 10 kilowatts. That typically includes your electrical installation, the installation of the inverters, your sales cost, your truck runs, all the overhead you have. And then we have an assumption, if we keep the 10 kilowatt system, a 10 kilowatt DC and a 10 kilowatt AC, what happens if we add more solar panels to the same system? So we go for 12 kilowatts or maybe 15. And we see exactly with a few samples how that will turn out and what the economics actually are. Jumping right into it, you don't have to look specifically at the numbers, but what I've done is I've designed 31 systems. All the systems have the same inverter, so the same 10 kilowatt inverter. That's this column here. And I designed a system that is 10 kilowatt DC, so a 1-to-1 ratio, 11 kilowatts, 12 kilowatts, all the way down to 31 kilowatts. And that, of course, is absolutely crazy. That's why there is a gray block over it. We typically only want to talk about systems from 1-to-1 to about 2.5-to-1, because from a code perspective, we will talk about that later, there are some limitations for these extremely high oversizing scenarios. The most important part is, and that's the outcome of the simulation, is how many kilowatt hours is each system with its respective DC to AC ratio actually producing over the course of a year. That's this column here, so we have the total yield so here from 13,500 kilowatt hours all the way to about 27,500 kilowatt hours. And the next column here is the efficiency of the system, so how many kilowatt hours per kilowatt DC installed is the system outputting. A graph will show a lot more than just a few numbers in a table. When we start at the efficiency of the system, that's typically a very common comparison model. We have the kilowatt hours per kilowatt peak. And we have here the kilowatt hours per kilowatt peak exactly. And on the x-axis, we have the DC to AC ratio. Or in this case, just the size of the system from 10 kilowatt on the left all the way to 31 kilowatts on the right. And what we see, and that's totally obvious, if we have very little oversizing, so we have a 10 kilowatt system DC on a 10 kilowatt AC, we have almost no loss. And the same applies to an 11 kilowatt system and maybe a 12 kilowatt system, and the curve is more or less flat over here. The more oversizing we have, the more curtailment losses, so clipping off the inverter, will occur, and the lower the actual efficiency of the system will be. At the same time, we can print the total kilowatt hours per year on the y-axis here, also over the DC to AC ratio. And we see if everything would be perfect, we would have a linear curve that just follows the bottom end of that curve. But the curve is having a little bit of knee, so the more curtailment we have, the lower the curve here will just drag into a flat part for even more oversizing. That's not super interesting. The real interesting part is how the economics will react to the oversizing. Next step is, for that sample system, I have to mention the sample system is a system that is just south-facing only. And in my case, it's just the two SMA 5 kilowatt inverters. When we assign the $2,200 per kilowatt as a sales price, and for your market that might be higher, other markets are lower. You can also use the price after rebates. It doesn't really matter because later on we will see the curve and the shape of the curve will be pretty much the same no matter if you're selling at $3 a watt, so $3,000 per kilowatt, or if you are in a more competitive market like an Alberta market or like an Ontario market where a lot of solar installers are competing for the same customers and the pricing is a little bit more aggressive. For the extra kilowatt that you add to the system, you typically only assign three things. You have to buy more solar modules, you have to buy more racking, and you have to install the solar and the racking. Everything else is already covered in the first 10 kilowatts. What we have here is then the system cost. that is calculated based on the $2,200 for the base price, plus whatever excess solar panels we added to it. And then based on the feed-in tariff rate, or it's not feed-in tariff, but it's the equivalent purchase cost the customer would have if he would still be grid connected, in this case 18 cents, we can calculate a return of invest. And that's exactly that diagram. What we have here, we are roughly in the range from about 11% ROI to maybe 12.7%. And on the x-axis again, we have the DC to AC oversizing ratio. So two things are right away obvious. If you have no oversizing, your ROI is not very good because you spent a whole bunch of money on the inverter, on the install, and you're not really utilizing the entire system based on the ratings of your solar panels. Because for the majority of the time, your solar panels that are rated under standard test conditions, STC, are not outputting nameplate capacity. The sun is never perpendicular to the panel, the temperature is never perfect, and that leads to not a perfect utilization of the 10 kilowatt inverter you have purchased. The other crazy part, of course, you can see is if you have extremely high oversizing, so to the 25 kilowatts, so 2.5 to 1, or even 3 to 1, the ROI is also going down. So having these 2 points, we will see obviously there's a peak in the middle where from a customer perspective, the payback of the system is the lowest and the ROI is the highest. And the real interesting part is now that it's probably higher than what most installers think when they design systems. A sweet spot when we say we want to have, let's say, 12.5%, and that's just roughly the same, doesn't matter if it's 12.7 or 12.5, from about 1.4 DC to AC, so 14 kilowatts of that on that 10 kilowatt system, all the way to about 23 kilowatt system. The return for the customer is roughly the same. And if we put that in years of payback, it's even more obvious. For the customer, it doesn't really matter if the system is a payback of 8 years, or 7.9, or 7.7. For the customer, it is, that's ballpark 8 years. But you can use that as a tool to really optimize your system and address maybe a consumption of a customer that has, let's say, 20,000 kilowatt hours a year, but you're constrained by the utility company not giving you enough capacity, you're constrained by electrical panels, we'll talk about that later as well, and really optimize your system for best economics. When we look at that, I have a quick takeaway sheet. The number one message is, yes, there will be curtailment losses. It's not perfect. If you have high oversizing, you will be operating at 10 kilowatt limit and you will lose energy. The other message is the loss of energy is actually not that great. And high oversizing makes economic sense when you put the physical installation and the yield of the system and the economics of the system together. And then from a customer perspective, the payback time for the customer doesn't really change a lot, no matter if you operate at 1.3 or 1.4, or even a 1.8 to 1 ratio, which for a lot of installers in the first place seems a little bit weird to go with 1.8 to 1. Jumping into another interesting part. So the first analysis was a south-facing system only. With a south-facing system, all the power that is typically curtailed happens around noon because there you have the peak and the entire system is only facing one direction. What happens if we have a multi-orientation system? The craziest multi-orientation system is a hard east-west because we have a curve, let's say half the system is east-facing, we have a curve in the morning where we have higher power, then a little bit delayed, we get the curve from the west-facing system. And if we look at the entire curve over the day, it's a lot more smooth and doesn't have as high of a peak around noon because we have earlier production in the morning and later production in the later afternoon. And one thing we see right away, again, the red curve is our efficiency. And you see a little bit in light gray behind, that's the graph we had before from a south-facing only. And the first analysis is east-west facing system is producing less than a south-facing. Totally obvious. So the curve starts already a little bit lower. The other thing you can see if you compare these two graphs, that the decline in the production and the efficiency on the red curve versus the decline on the gray curve behind from the south-facing system is actually less severe based on the effect that I have these two curves separated by time of day. And then if we draw the whole thing again for the kilowatt hours over the course of the year, so here on the y-axis, again over the DC to AC ratio, we get the total yield of the system. And here we don't reach all the way to maybe 27,000 kilowatt hours. We are a little bit higher based on those production constraints due to the orientation of the system. So lower curtailment losses in an east-west facing scenario, and generally lower yield for east-west. Same math now for an east-west facing system. We're installing the same panels, we're installing the same inverters, it's the same work to sell the system, no matter if the customer has a south-facing system or south-facing roof only, or it's, for example, a small commercial building where they have actually an east-west. And when we go straight into our graph, we see that, first of all, the ROI is lower because the system is producing less in an east-west facing, and we see a little bit of shift in the curve that the peak in our economic efficiency is actually more towards even higher oversizing. When we look into a summary, the more orientations you have from an oversizing perspective, the better it is because you have less curtailment. And for example, if you have two sides and you have 50% of the solar system on one and 50% on the other, it makes sense that in case of two inverters, that you have always one string from the east side and one string of the west side on the same inverter, because otherwise you're not utilizing that smooth curve where you have less curtailment losses. If you would pick a 5 kilowatt inverter only for the east facing and a 5 kilowatt inverter only for the west facing, then each inverter will peak with the entire capacity either in the morning or in the afternoon, but you're not sharing the advantage of the both sides and the orientations. Again, high oversizing makes even more sense compared to a south-facing system. And that's specifically important not only for a small sample, like a 10 kilowatt system, it's specifically important for commercial flat roof systems. So now, since Nova Scotia has on the radar up to 1 megawatt of commercial systems, having a system that has a high penetration on your roof, so you get as much solar on the roof as possible versus, let's say, a south-facing system only, where you then have an inter-row gap, and then you have the next row of panels. You can use an east-west facing system at low tilt to get even more power on the existing space of that customer. And that can be balanced now with the sizing of the inverters, with the available size of the buildings, and of course the load the customer has. And again, from an economic perspective, it doesn't change much if you have 11% ROI or 12% ROI, that's also roughly the same. Maybe one addition to the curve here. If you sell the system for more money, the customer has to spend more, and from an end customer perspective, your yield is going down. So what was here now maybe 12.5% may only be 8.5% if you're fortunate enough to sell for higher prices. The main message is, no matter how much you sell it for, the shape of the curve remains the same. It's just moving up if you sell for cheaper, or it's moving down if you can get a little bit more money from your customers. So the first point of view we had was always from a fixed inverter size. So we had a 10 kilowatt increment. And what we did, we sized up and down the solar system. So we added more panels and looked what the outcome is. But we can also look from the opposite side and say, okay, excuse me, you can look from the inverter size and have a fixed solar system. Typically, when you have a customer, the roof is the roof, and you can only fit a certain number of panels on. And that's just the maximum the customer can put on. But you have a chance to change and select the inverter to match that fixed roof system. And here we come directly to a different topic a little bit, which is directly related. When we vary the inverter size, we typically, from an installation perspective, are looking at what can the infrastructure of the customer actually take. And most most customers have either a 100 amp service and maybe they have a 200 amp service, and different on their system, they may or may not have to change the electrical panel. An electrical panel change is a big deal for a customer who just wants to have solar because he didn't know he needs a new electrical panel in the first place when he thought about reaching out to an installer to get solar. So giving this guy a new electrical panel at a couple of grand or even more money, depending on what your electrician is charging you, doesn't add any value to the customer solar system. It just makes the solar system more expensive. So understanding over the next slides how you can use the available capacity the customer has with the existing electrical panel. Let's assume it's not 50 years old, but maybe 10 or 20 years, the typical homeowner. You can calculate backwards how much inverter capacity can actually fit in that existing infrastructure. The electrical code was changed in 2018, and now the 2021 code has that in there as well, that you can have up to 120% if it's commercial busbar rating utilization, which means we have, maybe here, we have the main breaker. In this case, it's a 200 amp example, and we can add another breaker for two sources. One source is the grid, the other source is the solar system. So for commercial, as I mentioned, it's 120% the rule. For residential, it's even better. They allow up to 125%. So when we look into the calculation, how you size your breaker that can be placed in that electrical panel, we have the busbar rating of the panel, which is typically either 100 amp in most cases, sometimes 125 amps for newer panels, or a 200 amp for the bigger installations. You multiply that by 1.25, and you subtract the main breaker rating, and that gives you your inverter breaker. Let's do a quick example for the most common electrical system in Canada. It's a 200 amp service, which has a 200 amp busbar. It has a 200 amp main breaker, and if we do the math, 200 times 1.25 is 250. We subtract the 200 amps that are already coming from the grid. So you have 50 amps available as the breaker size according to 64-112. Since the solar inverter is considered a continuous load, or production in this case, you have to size or upsize the breaker. And if you have a breaker sizing factor of 1.8 that you apply, you get only 40 amps of usable current for your inverter. If we multiply that with a standard voltage here at 240, 40 times 240 volts gives us 9.6 kilowatts. So what have we learned? If a customer has a regular home with an old panel, and it's probably not one of those specialty panels, they can accommodate almost 10 kilowatts before you have to go in and change the electrical panel. As a very quick overview, I have the four most common combinations. We have the 100-100 as the top. That can only give you about a 4.8 kilowatt inverter. That doesn't really exist at the moment. The 125 is already a more suitable option. You can go up to 9.6 kilowatt. And if you have a 200 amp busbar, as we just did the math, you can go to the same 9.6. But the real sweet spot for new builds, for example, or new installation is actually a 225 amp busbar with a 200 amp service. And that gives you plenty of capacity that you don't have to do anything, and you can install even larger solar system on existing infrastructure. So in this case, it would be up to two 7.7 or 7.6 kilowatt inverters, which is a very, very common power increment in the industry. So understanding that not only is it from a financial perspective what equipment you buy, but if you look closer what the customer already has, you can save the customer $2,000 or $3,000 just by looking one more time at the electrical panel and selecting the inverter that fits exactly in that existing infrastructure size. For example, you can put a 7.7 kilowatt system in on a 125 or 200 amp busbar, and you size the system to 10 kilowatts. So there you have a 1.3 ballpark to 1 DC to AC ratio, or you even push it harder that you put 1.5 on. When it comes to oversizing in general, you saw the crazy numbers up to 31 kilowatts. That's not something I would recommend, and there are also certain limits from a code perspective that does not allow that today with current panels and higher amperages these new higher wattage panels actually have. But my main message is take that as an idea to go back to your simulation tool and try out systems you already have or systems you're designing for customers, and maybe put a bigger or smaller inverter in, or more solar or less solar, to get a feeling how the impact would be on the yield for your specific designs, and how you can utilize that to be more competitive in the market, maybe to other companies you're competing with, or just to save the customer additional money for not really any value if you upgrade the electrical panel for them just because they want to have solar. Jumping into the question, where does the power actually go when you curtail? And I heard the wildest kind of explanations that the power is absorbed in the inverter, there's a big resistor in it, and it will be turned into heat in the inverter, and that's why they have fans and all kinds of stuff. And the funny thing is, even 10 years later, I hear the same stories. So I want to take the opportunity, specifically with a presentation about oversizing, what actually happens to the power, and that none of that stuff is actually true, what I just said. We take the same sample system I had at the beginning. We have, let's say, a 12 kilowatt system, and a 12 kilowatt system under STC conditions, for example, would give us that blue IV curve. So the IV curve is pretty much defined by the specifics of the panel, your layout, how many panels you have in series, as well as the radiation that is currently hitting that array, and that gives us that curve. And on that curve, the operation points of the inverter will always move, and it has to be somewhere on there. What a normal inverter would do if it's not clipping, so let's pick a 15 kilowatt inverter, so we have plenty of capacity, the inverter will pick the maximum power point. That's exactly where the product of the current, the 41 amps in my example here, and the voltage is the maximum, and that's exactly the red curve we're seeing here. So left of that peak, we have lower power. On the right side of that peak, we have lower power. So the inverter's MPP tracker would pick exactly that point at 12 kilowatts, and the system is just working as is. Question now is, if we introduce, instead of a 15 kilowatt inverter, a 10 kilowatt inverter, we have that 1.2 to 1 DC to AC ratio. So something must happen that the inverter obviously cannot operate at 12 kilowatts because it's only a 10 kilowatt unit. So we have the same IV curve because the solar system on the roof didn't change and the weather is still the same. What happens now is that the inverter has two options. The inverter can even move out of that maximum power point towards lower current, towards the same current and lower voltage. That's going left. Or it can go to the right on the curve and has slightly higher voltage, but significantly lower current. And that's exactly what solar inverters are doing for at least the last 20 years. They always move to higher voltages and towards the open circuit point, which is pretty much here when you extend that IV curve. So let's go over the process that the inverter would do. So if we have a 10 kilowatt inverter and we assume the efficiency is about 97% or 97.5%, we need, of course, more input power than is coming out on the other end. With 2.5% efficiency loss, we need to add 250 watts that we can get the 10 kilowatts out of it. So that's already the point where we need to find an operation point that gives us exactly 10.2 kilowatts. What the inverter is now doing, it looks for a new operation point on that right side of the curve, and it will move slowly but surely down that ramp until it finds a point where the voltage is higher and the current it gets from the same solar system is exactly that 10.25. And that happens pretty much in no time. So current goes down in IV, and that's how we get to that curtailment. And in my case, I just did the quick math. The voltage goes up from about 295 in this example to about 330 volts. But at the same time, from a 41 amp level, it goes down about, 25% to only 31. And the product of slightly higher voltage with significantly less current gives us exactly the 10.25 kilowatts. So the power doesn't even exist in electrical terms when that curtailment happens. So the operation point is then just an operation point and no longer a maximum power point because it's not operating in the maximum power point. If anyone has used a IR camera on a solar system, on solar modules already, you can detect faults of a system based on temperature of the modules. And that's exactly what you can see with a system that is curtailed versus a string that is not curtailed, that the panels and the segment of the system that is curtailed, or not operational at all for that matter, is slightly warmer than the system that is actually running and delivering power at full capacity to the inverter. So that's a little differentiator. Good. Jumping to the second part of the presentation, and that's the global MPP tracking as a main topic. We want to look into a software solution versus a hardware approach, and we can go right into it. So first, before we go into the fancy algorithms, we want to just check what happens to a regular system and what's the status quo for any string inverter on the market today. Doesn't matter which brand, doesn't matter where they're coming from, China, the US, Europe. We typically have a string of panels, and the string of panels will create a string, a voltage, a higher voltage. So the voltage rises, and in this case, for example, if we are at open circuit, we are roughly here in the 380 volt range. The properties of the IV curve is still defined by the panels you buy and how you arrange them on your roof, in what kind of string design, and of course, the weather scenario. And we have, as in our example before, a very, very smooth IV curve. And that's important later to understand the actual MPP tracking algorithm. The inverter, as we discussed earlier, will just pick the maximum power point and will operate exactly there. No secret, super easy. Now we have a very hard shade scenario. So every module you buy for the last probably, or you bought in the last 30 years, always has bypassing diodes built in. For the most common panels, you have about 3 bypassing diodes, 1 for each segment of a third of the panel. So whatever 10 cells down, 10 cells up, that gets 1 bypassing diode. So 3 is the average. There are modules with more and modules with less, but 3 is the average. So what happens now is we have a hard shade that can be either snow is on the panel, or a neighboring building is casting a shade early in the morning or late afternoon, and the power of that panel goes to 0. So all the other panels are still working at full capacity, but this one is at 0 power. The inverter just moves the operation point, which was somewhere here in the previous slide, and just reduces the voltage to the power, or to the point where you have the voltage of all the remaining panel plus the forward voltage of the bypassing diode, which is point something volts. We just ignore that. So it's just the remaining voltage of the panels that are actually producing. And that doesn't require any fancy software. That's the case for at least 30 years, and it works for every single system. So what you get told by some manufacturers that sell a certain technology where they are interested in marketing for microinverters or optimizers, they of course don't tell you that because they want to sell you an optimizer. The DC current remains the same because this curve is exactly the same. It just is pushed a little bit to the left. And we still have the same smooth IV curve with a very, very clear MPP point. Now we can have a more sophisticated shading scenario where it's not exactly clear that you have a hard shading on, or shade on 1 or 2 modules. You have some kind of diffuse, half, maybe the panel is half covered or some dirt is on it because whatever happened to the system. Now it's a little bit more complicated. We have still no full dominance of the weakest module, because our IV curve now looks a little bit different. The IV curve now has 2 of those knees. We have the older IV curve we saw previously, that is for the unshaded panels only. And we have the new IV curve knee at higher voltages, where we consider the entire voltage of the string. So now we need an algorithm that can detect what is actually my maximum operation point on a global perspective. So not only a small area between, let's say, 300 and 350 volts, but we need a system that is able to sweep the entire input voltage range of the inverter. So typical string inverters today have a very wide input voltage range, typically from 100 volts to about 550 if it's a residential, or if it's a commercial system, we are probably at 250 to about 850. So there's a wide range where the inverter can pick different operation points on that provided IV curve. So now the inverter is checking. This is the operation point I would stay if I would do nothing at all, because that's the old point at roughly 300 something volts I was before. But now with that sweep, the inverter is checking every single point of that curve, or on that curve, and every single point on the power curve as well. Is there a point where I get more power out of it? And obviously, operation point number 2 has a higher output power than operation point number 1, sorry, than operation point number 2. So the inverter is smart enough to then decide that I much rather operate in operation point number 1 because I get more power out of it compared to an operation point at slightly higher voltage but at reduced current based on the shading effect or soiling effect I have from these modules. Exactly, so the algorithm has multiple names. The most neutral name is global MPP tracking, global for that it actually scans the entire input voltage range. One vendor out of Germany, SMA, calls it Shade Fix. Fronius, Bilal is here, calls it Dynamic Peak Manager. But the underlying software and the implementation is pretty much identical from a technological perspective. So now the main question is, when do I use, or when can I use an algorithm over deploying additional hardware in form of optimizers or microinverters? And a general rule is a lot of systems are installed where you do not have too much obstruction or many obstructions. You might have the odd chimney here or maybe a neighboring tree that casts a shade in the early morning or late afternoon, or seasonal shading that only in the winter you have a cast, but in the summer it's totally fine. That's a perfect example where you do not have to spend extra money and points of failure in your system by deploying microinverters or optimizers. So the algorithm itself will do perfectly fine. And that's the majority of the solar systems you install today. There are cases where you have more complex shading, where you have all kinds of obstructions and trees in neighboring buildings and elevator shafts and whatnot, where it makes it more complex. There you can decide if you want to go one or the other. And then we have, of course, extremely complex scenarios where you have shade pretty much all over the day. And then the algorithm can only do as much, but at that point, you would go with a typical optimizer to have a panel-level optimization further. I don't want to go too deep into it. There's a study from a university in Denmark. Instead of posting the actual URL, which is quite long, if you type into Google the impact of optimizers for PV module, you find a document that goes through all these different shading scenarios with poles in front of a system, covered solar panels, and they compare it from a normal inverter, an inverter with the global MPP tracking algorithm, to a solar edge system, which is a optimized hybrid, in this case, optimized string. And you can see exactly on that document what is working well in which scenario.
Another question.
Sure.
In this picture, is this indicating that Shade Fix is outperforming conventional module?
That's correct. That's correct. And that's exactly the outcome of that study. I have a quick personal story. I've installed a solar system on my parents' place in 2011 in Germany, and Shade Fix is nothing new. It exists already for, I think, 10 or 12 years. Yeah, probably 12 years now. In the European market, it just never really had the advertising in America, because it's much easier to sell a solution in form of, oh, I give you an optimizer, all your problems are fixed. That's much easier to explain than explaining how the algorithm works. And that system I installed in 2011 has that algorithm already implemented, and it was implemented ever since, and it works absolutely perfect. And if you look into the actual study, I highly recommend spending 10 minutes at the cottage to maybe look into that. It's very, very interesting how the different scenarios work out in favor of an optimized system or in favor of a normal inverter with MPP tracking algorithm. It's very, very interesting and not typically what people think it is. So if we look into the limits, so first of all, if you have heavily shaded and very, very complex scenarios, my question would be, is this really a good solution or a location to put solar on? Maybe it isn't. So you can still do it, and if your customer is happy to pay for it, might still be a business case, but in most cases you want to put panels in the sunlight and not where they are heavily shaded. And if you have such a scenario where you're not sure or it's very complex, just use optimizers or microinverters. Easy way forward. When you have seasonally or only partially shaded systems, so systems, as I mentioned earlier, If it's only shaded in the early spring or in the winter, and it's not shaded in the summer, this is a perfect solution without adding any components. Roof ridges, so different roof elements casting shade on other roofs, neighboring buildings that are higher, that are higher than yours, larger trees from your neighbors, elevator shafts on commercial are typical issues, and then the seasonal inter-row shading if you have a ground mount system or a commercial rooftop system with south facing only and a certain bigger or smaller inter-row gap. That also works very, very well. And pretty much all the inverters today from the bigger brands, no matter if it's Fronius or SMA or CSI, a Canadian solar inverter, they all have that algorithm in one form, but probably with a different marketing name. The string layout and string length. So you can only activate bypassing diodes when you have voltage room left on the bottom. So you really want to optimize your design, generally with every string inverter, to have a voltage that is as high as possible. Because if you have, let's say, 10 strings in series, if you have shade on 3 of them, and you cut them out by using the bypassing diodes, the 7 remaining panels are the voltage you get. So if you already only have a string that is very short and very inefficient, if you have a string of 5 and you cut 3 out, there is no voltage left for the inverter to operate. So general idea is keep the strings long. The efficiency is very good for the inverter. It operates better, it saves you cost on the home runs, and the algorithm will work better. So positives on all the points. And then, as I said, you want to have an inverter that has a very wide input voltage range as well, which, again, most inverters today have that. A few key takeaways. The main message, a string of solar panel is not affected by the worst performing panel. It has never been true since the introduction of bypassing diodes. The thing that is affected is mainly the affected panel. The rest can operate with a normal string inverter. All MPP tracking algorithms today, no matter which inverter, already manage hard shading or even a module defect. So if a module has a crack in the glass or has water ingress or something like that, as long as the bypassing diodes, that's why I have a little footnote here, is intact, the panel will just be not used in the system and the current will flow around the panel and the rest of the system is unaffected. The advanced algorithm, global MPP tracking, checks the entire voltage range and always selects the highest operation point, no matter if that's at higher voltage where you started, probably with an unshaded system, or it actually has to push down the voltage a bit to find a point where the system has the best output power. And then, from a design perspective, a regular string inverter, most of them come with multi-MPP trackers today, work for the majority of rooftop designs. And in most cases, outperform more equipment. So the best systems, from a design perspective and from a reliability perspective, are always a system that has the least amount of components. It's not getting better if you add 20 or 30 more components that for a majority of systems you don't actually need. Yes, I know it's convenient. And yes, the customer gets some fancy app on his phone to check what panel number 17 is doing. And maybe it's performing 5 watts better than panel number 16. But that's not really the value proposition long term for the owner of the system. Yep. That would be the presentation. I'm very happy to address questions because the questions are typically what is the exciting part. Yeah, go ahead.
Have you done a study with the DC to AC ratio that you originally done with bifacial modules instead?
So bifacial modules act like a higher DC to AC ratio because you have some gain, whatever much that gain will be, from the backside. So it's very, very hard to simulate bifacial because none of the software solutions are really on point to quantify bifacial because there's so many factors that go in and you cannot rely on, let's say, an STC flash test, no matter if it's a front flash test or a back flash test in addition. So it's mainly from an engineering perspective at the moment just a ballpark number. So people have installed a few systems as tests or even in full large-scale deployment, and they come out with, let's say, 7% yield or 8% yield or 15%, depending on how much snow they have, what the inter-row gap is, how much what the racking looks like, if it's a landscape versus a portrait orientation. That has all impacts on the backside. So when we look at the oversizing analysis, what you would do with a bifacial, you just push the curve towards lower DC to AC ratios with that idea in mind that you get some power from the backside. So instead of 1.5, you just assume 1.4 would be the equivalent front side only operation. Go ahead, Woody.
You have microinverters that are operating at 97% efficiency, and your string inverter is at 97% efficiency. How is the string inverter with Shade Fix outperforming the microinverter system?
The main thing is the microinverter has a certain voltage range. And most microinverters do actually not activate bypassing diodes. So if you use an N-phase, for example, it's the best example because they do not do it. With APS, I'm not sure. Heumals, I think they can do lower voltages. You cannot operate at that ideal point when you only have, for example, 1/3 of the panel effectively shaded. And that's the main difference. So you can have this diffuse shade system at high voltage that a microinverter would work totally fine. And that would be that example I gave when you have very, very complex scenarios where you cannot make a string inverter work, for example, because you have only 2 panels facing one direction and a few other panels, a totally different orientation. It's just not going to work from a layout perspective. But from a conversion efficiency perspective, you talk about the peak efficiency, but if you look into the operation over the entire production curve, there's so-called CSE, weighted efficiency, where they look into what's the efficiency at 10%, what's the efficiency at 20%, at 50%, at 70%, at 100%. And that forms the overall efficiency. And typically at lower radiation and complex shade scenarios to the panel itself, the overall system works better where the inverter is, for example, able to only activate one of the 3 bypassing diodes and not just the panel itself. Yeah. And not every microinverter is at 97%. So some of them are even a little bit higher, but there are a lot on the market that are still in the 96% effective range. Yeah. And there's some inverters, of course, that are not 97.5. It was just an example. They are already 98, 98.5, and commercial even 99. So there's difference is even more critical. Yeah, go ahead.
I have a system that's 10% oversized on the array size, and I'm only coming up to maybe 10% underneath capacity of the inverter. I think I'd like to add more array. Do I have to put that at the end of the string so they're all coming in, or can I tee that in each of my strings?
That depends a little bit on your string design. So there are multiple options to approach it. If your system is older and the panels are older, you're probably not going to find the same panels. 2 years old, okay. Still, they're probably not available anymore after 2 years. What you can do are 2 things. You can either add a string that is very similar in voltage. So for example, you have a string of 10 60-cell panels. You can buy a 60-cell panel today with higher wattage, but 10 60-cell of the new type is still very similar in voltage to what you already have on your roof. That's the easiest. The other option is if you want to add modules to an existing string, what you have to pay attention to is that the new panel you buy has a higher IMPP rating than the panel you currently have. For example, you have a 9 amp IMPP right now for the panels, so buy something that is 9 or higher, so the new panels are not pulling down your old the old system. And that's very, very common actually in Ontario because people have these old systems and they have these microfit contracts where they make tons of money with feed-in. And some of the contracts, Bilal is smiling, they just try to figure out if they can make another $5,000 a year because panels are super cheap today and the payback times are just enormous. They have typically 1 year, 2 year ROI or 50% ROI, which is just, perfect. Go ahead. Yeah.
So when you were preparing your simulations for the clipping
Mm-hmm.
with your higher DC to AC ratios, how did you figure out how much is being clipped off with each?
I actually even listed, so there's a so-called PR ratio, so performance ratio, that puts the potential yield with the actual yield in perspective. Let me quickly go back. And there you can see actually what clipping losses you have.
Just a heads up, it's probably the last question.
Yep. So here, for example, we have, at perfect conditions, we have a performance ratio of 88%. That's, in a real-life scenario, already very good. Most systems operated probably 80% as a good operation point. The more oversizing you have, the lower that PR ratio will go, all the way down to about 60%. And the delta between the 60% we have here and the 88% is exactly your clipping loss.
Okay.
Or if you look into, that's probably easier to handle, the specific yield in kilowatt hours. What used to be, let's say, a 1300 kilowatt hour per kilowatt peak system is now becoming just a 900. So the efficiency is going down based on the inverter being at its max and not being able to use the excess power.
So did you calculate that yourself, or was it like a
So this is simulated with 3 simulations tools, actually. The main simulation in the data here, I just picked one for data consistency, is with the SMA Sunny Design. That's a free tool you can use online, open to anyone, and you can use it also for other inverters. It's pretty much neutral. You can use it. The same string layout would work on a Fronius, for example. And I checked it with Aurora. So they're very, very similar. So we talk about probably 0.5% up and down in the actual numbers. But the general scope is exactly that reduction of performance. Thank you very much. I'm here for